I used to sit there for hours as a kid playing with magnets. I've always been fascinated by them. That imaginary force that pushes and pulls. It's always fascinated me. I always used to think when I was a kid whether or not I could levitate two magnets. I used to sit there for some time trying it, but I soon came to realise that either it was impossible or my hand just wasn't steady enough. Probably the latter. However, as I got older, I soon came to realise that this magnetic force between these two magnets increased by the square of the distance, meaning that basically it gets faster and faster and faster. So if you was to find this sweet spot with two static magnets, a mouse farting 100 miles away disrupt it, which basically means it's impossible. There are people out there who claim they can do it, but in free air on planet Earth it's near on impossible. There's even equations that prove it. However, there are different ways you can do it, usually using an electromagnet, and I thought I'd build up a circuit. So I was done a bit of theory, had a look online, and you know, most of the circuits out there are not that simple. So what I aim to do is come up with a circuit that basically a 3-year-old should be able to put together. Well, I might be exaggerating there, but a non-electrical engineer could easily put it together and understand how it works. So we look at a little bit of theory now, I'm afraid, before we get into good stuff. But it's not theory of magnetism, so don't worry about that. It's just a basic theory of the control system that we're going to need to levitate the magnet. So, what problem we face with? So, if we look at the dashed line here, that'd be the sweet spot that I was talking about. So, you know, anything above that sweet spot, we're going to lose the magnet. Anything below it, we're going to lose it. It's going to fall or it's going to snap into the other magnet. So if we was to have a system that could detect when it's coming up close or going past the sweet spot and control the current that flows through the electromagnet, we should be able to levitate the magnet from underneath here. So we're going to need some sort of feedback system that can detect this. So this wavy line here, you can imagine that wavy line would be the magnet, and this appeared to be the electromagnet. So basically, I'm exaggerating the distance here obviously, but so if we got up to this point, we'd switch the electromagnet off and the magnets start to fall. If we get past the reference point, we'd switch the electromagnet on, which would bring it up closer, and just repeat that process, and we should be able to get magnetic levitation. So let's have a look. So what I'm thinking is, if we was to put a sensor underneath the electromagnet that could detect the magnetic force of the static magnet, we could feed back that information to, say, an OpAmp. I'll show you the circuit in a minute that I've come up with. So what I was thinking of using is a Hall effect sensor. This is a linear type. They come in two different flavours. This basically, the output voltage is a function of the magnetic force, so it'd be like a linear increase. That's the one that I'm using, but the other one that you can get is basically like a digital switch that just switches on and off. There's no voltage variation coming out the system. So if we was to have that under there and detect the magnetic force, we should be able to control the system and levitate the magnet. So Right then, let's have a look at the circuit diagram. Right, it's very simple. I don't know if you can see that there, but I'll just have a little chat through it and I'll zoom in on it so you can take a look at it. So basically the system consists of an LM358 OpAmp in a comparator configuration. So on the non-inverting input, we got the reference from the 10k pot. My system happens to be 4.5 volt DC, so that's a reference I need in this system on this actual electromagnet to find the sweet spot. And then the inverting side, we got the Hall effect sensor connected to it. Basically simple as that. So how the system would work is, so initially before the static magnet is in contact with the electromagnet, the reference voltage is going to be higher than the Hall effect sensor non-inverting input. And then as we get closer to the electromagnet, this voltage will rise obviously, and then the difference will be outputted. So if we get to a certain point, the magic spot, as you like, these two voltages will be basically the same. And obviously if we go too far, the Hall effect sensor voltage in there will send the output low. So what else can I talk about this circuit here? Yeah, D1, the diode going across the coil of the electromagnet, that's very important, because whilst it's switching, as it switches off, there's going to be like a massive voltage build up, and you don't want that going through the your Mosfet. So if you put the diode across it in that configuration, it will basically dissipate all that voltage down to a safe level that's not going to damage the Mosfet. So yes, R1E, probably notice R1E, the 220k resistor. That is not mandatory, but it's in there just to add a little bit of hysteresis. So if any of you don't understand what a hysteresis is, I've scribbled down on a bit of paper so you can obviously try and get a bit of an understanding. So what I've done, I've just exploded the reference point out. So basically between these reference lines here, that basically this is where we want the op-amp to float. But if there's any noise on the system, it's basically this noise here is going to take it above the actual reference, and you're going to get some false triggering. And this was apparent in my circuit actually, which you'll see later, because the actual conductors that are connected to the Hall effect sensor was acting a bit like antennas. So I'd switch my fluorescent light on that I got in this room, and basically the magnet would freak out and lose its levitation. So with that, with this, I've calculated this, but this 220k should suit many systems if you want to use it, if you're having issues with oscillations and whatnot. As you can see, with no hysteresis, with the noises on there, we're sort of getting false triggering on the output. And with the hysteresis, basically it cleans this wave up, and we're only going to get the output that we need. Because if you follow the line in here, basically with the hysteresis, what we are looking at is probably that sort of wave here, rather than all this mess, if you get what I'm saying. So that's why we've added the 220k resistor. So that's from the inverting input to the output, just to add that little bit of hysteresis. So have I missed anything out? I think not. Hall effect sensor needs to be mounted face down for it to work in my system anyway. The electromagnet, I wound it myself. It's got an iron core. Basically I got 300 turns I believe, with a DC resistance of 20 ohms. One thing you've got to take note of though, you must, if you do wind your own, take a resistance reading, figure out what your maximum current draw is for your Mosfet or transistor you're using, and accordingly current limit it with a resistor at the right size and power rating. And that's about it. So I think that's all the boring stuff out the way. So I'll just have a quick zoom in for you on this so you can have a look, and then we'll fire up the system. So there's a circuit built up on a bit of perf board. So we've got the 10k pot, we've got the OpAmp, we've got the Mosfet, we've got the diode behind the scope probe there, and we've got the 220k hysteresis resistor. I've added a bit of capacitance across the DC in, and that's 470 UF, and a 0.1 UF going across the supply of the OpAmp. That's just helping, you know, if we get any glitches in the DC in, it shouldn't affect the system. Take no notes of the piece of wood on there, that's another project. I'm just using that just so I can perch the electromagnet on here. So there's the electromagnet. Like I said before, there's about 300 turns on there. We got the Hall effect sensor mounted underneath there. A little tip, I've managed to break 2 or 3 of these when I was just resting on the top, well, smashing the magnets into it while I was tuning. So if I was you, I would sort of poke the Hall effect sensor up there and protect it away from any damage that would be caused through the magnet smashing into it. So there you have it. So we got the coil, that's the actual main coil, and then the 3 conductors coming out for the Hall effect sensor, which is power, ground and out. And so let's do a little explanation of the waveforms now before we float the magnet. Yeah, so channel 1 we got there, which is the yellow trace, that would be the output of the OpAmp. We got the blue trace there, which will be the reference voltage, and the mauve one, you can just see it underneath there, that would be the output of the Hall effect sensor. So as you can see at the moment, the output of the Hall effect sensor is a little bit lower than the actual reference voltage. So if I was to bring the magnet up close to the electromagnet, you see that the actual Hall effect sensor's signal is higher, which will take the output lower. And what our aim is to line these up perfectly to find that sweet spot and levitate the magnet. So let's start some levitation. So the moment of truth. You do need quite steady hands so to get it levitating, but once it's levitated it should sit there forevermore. There you have it. So yeah, I think it's very stable considering I'm only using a single op amp and a couple of components. It's not bad at all. So we look at the, so take a look at the waveform. Yeah, so the system pulls around 87 milliamps at 9 volts, which ain't too bad at all. So you could run it off of a single 9 volt battery, but to be fair, I don't think it'd last long. So there's the waveform. So as you can see the reference voltage and the output of the Hall effect are basically on top of each other, which is going to be that sweet spot. And so I don't know if the keen eye can notice that, but if you look at the min and max values of the output of the reference voltage, you'll probably see that there's probably about a 0.5 volt difference between the min and the max, no, 0.6 volt difference between the min and the max, and that would be this hysteresis resistor that's in circuit. So basically it just gives it a bit of headroom, and so any sort of spikes coming from the Hall effect sensor should be ignored. Like I said earlier, I was having trouble with the fluorescent light in this room, and that seems to have cured it. So there you have it. So if anyone is interested in calculating a bit of hysteresis into their comparator, I'll share my calculations here, and you just all you need to do is just alter the values as required. So as you can see, I calculated where is it? My camera action's not very good. Yeah, so basically calculated in there 0.6 volt hysteresis headroom. So there you have it. So just have a quick scan over this. I don't want to explain everything on there. I think I've waffled on too much of the theory side of things, but basically what's happening is when the op amp is at a high value, and that 220k resistor is going to be in parallel with the actual voltage divider coming from the potentiometer, and likewise when it's at a low value it's going to be in parallel with R2, and obviously that will change the output voltage. So there you have it. Hope you enjoyed it, and I'll leave you with this.